everyone. I'm going to talk about something a little bit different from what's been so far. Less biology, more chemistry. I'm going to talk about the chemistry of the rhizosphere and more specifically about aeration treatments and how they affect the oxygen levels and the redox potential in the rhizosphere. So first, let me say why this is important for us. This is a distribution for a distribution of water irrigation, water sources for agriculture in Israel. As you can see here, that almost 50% of the water that we use for irrigation are treated wastewater. This is basically sewage water that we treat and then we bring them to a better quality and then we reuse them as irrigation water in agriculture. This water contain a higher content of salts, mostly sodium, which could be very problematic, and higher organic matter content. And they are, in general, they are regarded as of lower quality compared with fresh water. And when we use irrigation with treated wastewater for many years, what we have seen is that we witnessed a decline in yield. You can see here in the y-axis, this is the ratio between yield with treated wastewater to the yield with fresh water. Value of 1 means that there's no change. Okay? If we go below 1, it means there's a reduction in the yield of the trees. And on the x-axis, you can see the years since we switched to irrigation with treated wastewater. So the long we irrigate with treated wastewater, you can see a very clear decline in the yields. Here is for avocado and citrus. The most interesting thing about this is that the decline has been found in heavy textured soils, clay soils actually, and not in sandy soils. And it was found that the reason for this decline was oxygen depletion from the soil, from the rhizosphere. So what happens there? When we irrigate with water with high values of SAR, SAR is the ratio between the sodium to the divalent cations in the water, mostly magnesium and calcium in our case. So we irrigate with high SAR value water, and then we get expansion of the clay particles, expansion of the soil, and a reduction of the oxygen diffusion in the rhizosphere. At the same time, high organic material content in the water increases microbial activity. Microorganisms use oxygen for their respiration, and therefore, from these seemingly unrelated processes, what we get at the end is a depletion of oxygen in the rhizosphere, in the root zone. Oxygen, which is of course necessary for roots respiration, but also if we look at it from a chemical point of view, then a depletion from oxygen in our system means we move towards a more reduced environment and maybe get accumulation of reduced species that may be toxic to plants. So the aim of this work was really to test different aeration treatments and try to understand how they affect the oxygen levels and the redox potential in the rhizosphere. So we conducted an experiment in this avocado orchard in the northern part of Israel, western Galilee area. The soil was obviously a heavy textured soil, 40% clay. That's what we were looking for. And we had like 5 treatments, 2 controlled treatments, and 3 treatments that we checked for aeration treatments. control with treated wastewater irrigation, and control with freshwater irrigation. And then we had a treatment of low frequency irrigation with treated wastewater, where we irrigated only 2 times every week, twice a week, and not 3 times a week. So after each irrigation, the soil has more time to recover. The moisture content on the soil has the opportunity to decrease and therefore improve the aeration in the root zone. Another treatment was a mixture of freshwater and treated wastewater in a ratio 1:1. That's the purpose of this treatment was to improve the quality, general quality of the water that we enter the soil. And the last one was aeration trenches made of scoria rocks. That's a very common treatment for aeration in orchards, very common in Israel. We do it when we have problem with aeration in the root zone. So this is a scheme of how how we put up the experiment setup in the field. We had two sets of electrodes on each side of the trees. Each set of electrodes contained one oxygen sensor, one redox potential electrode, or a P electrode. And a quick word about redox measurements for those of you who are not familiar with this field. We can measure the reduction oxidation potential directly in the soil with specific ion-specific electrode, very similarly to what we do with a pH electrode. Only here we get a millivolt output, millivolt values output based on the Nernst equation, and then we can evaluate the reduction oxidation potential in the soil. All this equipment was connected to a data logger that was stationed in the field. We also had a solution sampler to directly sample solutions, soil solution, to measure the soil solution parameters and different chemical species that we were interested in. And all the equipment was inserted to a depth of 35 centimeters below soil surface. You can see a picture how it looked above the ground. So let's take it step by step and see what we found with the different treatments. This is the oxygen levels that we measured. Here are 2 weeks of measurements, and you can see here lines that represent the irrigation events during these 2 weeks. The irrigation lines refer to the 3 times a week treatments, not to the other treatments, so try to stay on that. If we add, I can barely see it, but if we add the measurements for the treated wastewater, what you can see is a very sharp decline every time, a very sharp drop actually, whenever we irrigate. A difference of around 5% in the oxygen in the soil pores. You can see it corresponds very clearly to irrigation events. The low values are around 11%. And if we add the freshwater treatment to see the difference between treated wastewater and freshwater in heavy soil, you can see that also here we see a response to irrigation events, but much milder. Oxygen values are generally higher, and the minimum values are not as low as the treated wastewater. Now let us see if one of our treatments did the trick. We can see the low frequency irrigation event. You can see that, first of all, you can see that it doesn't correspond to the irrigation lines that are drawn here. simply because these are not the irrigation times for this treatment. Like I said, it's been irrigated only twice a week, so it's a little different. But what you can see, there is a drop in oxygen levels after each irrigation. You can see that the drop is very sharp, like would be expected from this treatment. But you can also see that it has a lot of time to recover, less irrigation events, more time for the soil moisture content to decrease. What about the mix treatment? We can see it kind of looks like the fresh water, pretty similar, even with milder drops. But the big shot, maybe, is the tooth treatment. You can see that values of oxygen are very high. It almost doesn't respond to the irrigation. We know that the scoria rocks have very high porosity, and they are a very good treatment for aeration of the root zone. What about redox potential? Same colors. Let's go quick, go over this. You can see first that our two control groups, treated wastewater and fresh water, the difference that we would expect, there's a more reduced environment in the irrigation with treated wastewater compared with the fresh water, a difference of around 100 millivolts there. Low frequency irrigation and mix fall somewhere between, but the big enigma, the big surprise was the tooth treatment. And like we saw before, the tooth treatment had the highest values of oxygen. It had the highest amount of concentration of oxygen in the system. And still we see that here, according to the redox potential measurements, it is the most reduced. How is that possible? We'll try to answer that towards the end. A quick recap on redox and what it does in our system, in a chemical system. So once we have a depletion of oxygen, we start having reduced species. We have a lack of oxygen, we get reduced species. At first we have reduction of nitrate to a more reduced forms of nitrogen, and after that, when the system gets more reduced, we can also have reduction of manganese and iron, and in very reduced soils, we even get mostly waterlogged soils, not drained soils. It's hard to find a reduction of sulfur and carbon dioxide in drained soils. It's mostly in waterlogged soils. Accumulation of one of these species, even the manganese and iron, which are important nutrients for plants, accumulation of them in higher concentrations in the soil solution can lead to toxicity. I'll go over quick. So this is what we found with nitrate concentrations. You can see that in the treatment of the treated wastewater, we had significantly higher concentrations of nitrite, which is fit to what we've seen in the oxygen levels results, because the nitrification process requires oxygen to happen. When oxygen is a limiting factor, the oxidation of the ammonium ion to nitrate is not complete, and we get accumulation of nitrite in the middle. Manganese and iron were not significantly, we didn't see accumulation of any of these species, and the reason is that we're simply not there. As you can see, the values for the system has to be so reduced so we get manganese and iron, and we're just not there in this system. And I just want to 2 minutes maybe about this thing, because I think it is very interesting about the anomaly of the tooth treatment. How can the treatment has the highest values of oxygen and yet the most reduced values? So when we got that at first, we dismissed it as a mistake, maybe something wrong with the measurements. We try to check it again. That's what you do when you get results that doesn't fit to your sense, to your hypothesis. You say it's a mistake. You just dismiss it. But then we did it again and again, and then we got the same results again and again, and that got us thinking. And a nice quote from Isaac Asimov that I really like is that he says that the most exciting phrase to hear in science is, that's funny. So when you get something that doesn't fit your permissions, you shouldn't dismiss it, you should check it and go with it and see, maybe you'll find something interesting. And we took soil and scoria from the field. We packed them in bottles, as you can see here. We did a Marriott bottle experiment in the lab. We inserted We inserted a pH electrode and an oxygen electrode, and we started saturating the mediums, and we saw we tried to keep oxygen levels similar in both mediums, and we tried to see the difference in redox potential. And here you can see that for the time of the experiment, lines of oxygen, left x-axis is oxygen, right x-axis is redox potential. The solid line represents the soil oxygen and the tooth oxygen. And you can see that they were pretty similar. We managed to keep them pretty close. We started saturating the soil. At first they were stable, and then we started saturating the soil, both mediums, and then they started dropping. You can see that for the whole period, the redox potential of the soil is higher than the tooth. Naturally, it's higher. So that's something that we got also in the field. So, hey, it's not a mistake. We were happy. And then we put the redox potential against the oxygen percent. And then what we got is that, as you can see, in the high oxygen levels, the soil is more oxidized and the tooth is more reduced. Only when we reduce oxygen levels to around 15% oxygen, we get the inversion point. This we call the point of inversion, around 330 millivolts, which is the value for, if you remember from before, the reduction of nitrate to nitrite, this reaction. One last thing. So what we said is that, what we were guessing is that the scoria consists of reduced iron minerals, some magnetite, olivine, pyroxene. I hope some of these words say much to you, maybe not. And these reduced iron minerals they kind of buffer the redox potential at low levels, where in the soil, the redox potential is more a result of biological processes, for example, the nitrification, and that's why we see this sharp drop here at 330. Last slide. We saw that aeration treatments can increase oxygen levels in the root zone, essential for roots respiration. Aeration treatments can improve redox regime in the root zone and prevent accumulation of nitrite. And last, scoria, which is a very common aeration treatment in orchards, demonstrate relatively low redox potential due to the nature of its minerals. And I want to thank you for your attention, and for my group members for all the help. That's it.